Hi, I'm Chuck Brandel, Vice President and Engineer at ISG, and with me I have...
Hi, I'm Bailey Griffin. I'm a graduate engineer with ISG.
And we are going to present on successful strategies for storage implementation on public drainage systems for the 2020 MAWD conference. A little bit about ISG. We have 10 offices in 4 states, serve multiple markets. Myself, I am the leader of our water market. So starting off, the importance of public drainage. Most of the Midwest needs artificial drainage to support agriculture. Without it, we would not have the agricultural base that we do. Most of the infrastructure that drains our the prairie pothole region is old and was not designed for new farming practices. This infrastructure was built 100 years ago with numerous public drainage systems, and there's been very little update since then. A lot of these systems are failing, and there's a new opportunity to do something different as we replace these systems. The old drainage mentality versus modern design, when these systems were designed, water was the enemy. We were draining wetlands and shallow lakes to open up land for farming. There were health concerns, flooding concerns, no concern about sending water downstream, but they were designed for different farming practices, 3 to 4 different crops, small grains, farming land farming and harvesting over months instead of days or weeks. New drainage demands, we have bigger equipment, increased in pattern tiling, the need to improve and upsize these systems to handle the more intense rainfall that we're seeing. And the current infrastructure is not designed, but at the same time, we have water quality concerns, Gulf hypoxia, stream bank erosion, drinking water contamination, and altered hydrology with the loss of some of the wetlands that were drained 100 years ago. So looking at how do we do public drainage, there's a new area of drainage. We're looking at multi-purpose drainage management. What is multi-purpose drainage management? It is engineered drainage systems that utilize best management practices to increase agricultural drainage while improving water quality. For this presentation, we're going to emphasize on storage and the importance of storage on public drainage systems. We have new ways to design. We have better technology, we have better ways to model, we have more research, more monitoring experience. We have more data available with LiDAR, and we've seen what the benefits of storage can be. So when we look at technology, here's a modeling video. We have different ways that we can design better: controlled drainage, storage, bioreactors, saturated buffers, wetlands, water recycling, and other practices. This example of a XPSWMM model shows how we can put storage in a system and not increase flows downstream. And actually, for this project, the storage will decrease the amount of the size of our improvement by adding storage in the middle of the watershed. So how do we approach this? We start out by talking with the landowners. There's usually some sort of problem. A drainage system needs to be updated or has failed. We start out with a feasibility study, meet with landowners on site, look at different options, and then have an informational meeting with all of the landowners and the drainage authority. And then if necessary, meet with agencies. But all throughout this process, we need to discuss water quality and storage at every step and have that in place before we start a petition for a public drainage improvement. At the same time, we look at MDM plans, and we do an MDM plan up front to try to develop that list of priorities for BMPs, get landowner input before we start making some decisions, see if there's grant opportunities, and then look at where the infrastructure needs are, and are there things that could supplement that, storage, wetlands, or other practices. Sometimes putting storage in the right place can downsize an improvement downstream by not needing as much capacity. We review those results, calibrate the plan, and then hopefully implement MDM practices. Same time, we have to sell it. These are new practices, the new way to design. Sometimes it's difficult to get farmers to change their old ways. We are seeing a big change in that recently, and we are getting more buy-in for storage. Again, farmers don't like to see more water ponded, so you got to find the right areas and decide who gets the storage. Is there a low land that floods out routinely that we can utilize? Who's petitioning, who's in charge? Sometimes those are the people that you can target for storage because they see the benefit of getting the project approved. Is there any state or federal land available? Land sales can be different. We have utilized some existing easements to provide storage, and that can be cost effective. And sometimes timing is difficult. We've had some good projects that we've had to turn away just because we need to get the project moving and there isn't grant funding available, or we don't need a grant cycle. Again, some of the solutions are just being creative. Look for ways to do projects outside of the public drainage project. We have many private wetland banks that we are doing as part of drainage projects that are providing storage and water quality. And sometimes there are just small, easy targets that we can utilize, and maybe we do multiple drainage areas to provide compromises. Again, to get these approved, you need the right attitude and the right approach. You need to get everybody on board. The drainage authority needs to have a willingness to do it. And if so, landowners typically trust those local government units. So if they trust the drainage authority that they're willing to do it, we can usually get the landowners on board. Local contractors, the landowners really look to them. And if they trust that something works and we can show examples, that's important. SWCDs, it's an important part to get grant funding. And then just the board makeup and the ditch managers. If we don't have their support, we're not going to get approval of some of these practices. And then looking that there might be different ways to incorporate storage and water quality for each project. So how do we implement it? I mean, to do it, we have to show benefits, which means increased production, more capacity. We're essentially solving a drainage problem. At the same time, we're evaluating the downstream effects, the adequacy of the outlet, the water quality of receiving waters, and how much storage we need. Leads us to look at multi-purpose drainage management throughout the watershed. But we need to be cost effective with creative designs, trying to get outside funding. We need public landowner support. And it's important that we get partners involved. Sometimes these projects do not have the funding for research, but if we can find that in other places, we can prove that we can have successful projects. So we'll go over a case study for a very successful project, Blue Earth County Ditch 57. Let Bailey take over from here.
Yeah, right. So like Chuck said, we'll go through the case study for Blue Earth County Ditch 57. This is a prime example of how we were able to implement BMPs, including storage on the landscape successfully with many partners, and we were actually able to get some grant funding for that as well. In addition to getting those practices implemented, we were also able to get dollars to do some monitoring on the system to see the successful benefits of the BMPs in terms of water quality and quantity. So a little bit of project background. CD57 is located in Blue Earth County, which is a county in south central Minnesota. We can see the boundary, watershed boundary located in red on the image on the right. This watershed boundary for CD57 is 6,040 acres. This watershed is a little bit unique to southern Minnesota since it does include the city of Mapleton, so there are some urban aspects and rural aspects to this watershed. It's both a tile and open ditch system, which includes both of those drainage benefits. For this project, that system was designed in 1907, which in the 2000s, we're seeing major failures of that system, which is about 100 years after it was constructed. So there was a petition for improvement that was filed in 2007 from the landowners, and we came together with many partners, all of them listed here on the bottom of the screen, the landowners of CD57 County, ISG, MSU, DNR, MDA, MPCA, and came together with an approach that addressed both the drainage problems and also included many water quality BMPs. So it's a really collaborative effort with many partners. And through that, we were actually able to get a grant fund through LCCMR of about, Chuck, if you want to go to the next slide.
$485,000.
Yep. $485,000 to implement these BMPs. To do that, we were able to implement the Klein Pond, which is located just off of the city of Mapleton, a city pond expansion, which took stormwater from the city of Mapleton, two-stage ditch, and native buffer strips, rate control weir at the outlet of the system, and an overdug ditch. So we were able to implement and use that grant funding to get those BMPs onto this drainage system. And then also included in phase one was 3 years of monitoring that monitored the initial benefits of water quality benefits from those BMPs. Next slide. From those, we were able to include 9 monitoring points that showed initial reductions of flow reductions of 10 to 50% through the Klein Pond, and also showed captured sediment within the pond of 30 dump trucks worth of sediment. At the end of phase one, we were able to come up with those initial water quality benefits, but it also identified the need for continued long-term monitoring of those BMPs on drainage systems, and also raised questions of what are the maintenance efforts needed on those BMPs, and how much is that going to cost, and how often do we need to be able to do those? Which brings us to phase two monitoring. Next slide, Chuck. Which continued to be a collaborative effort with all of our partners, with information sharing and different people doing different parts of this project, which we're really grateful for. And during phase two, we were able to get an additional $105,000 to help do continued monitoring for an additional 2 years, and develop some maintenance schedule recommendations, and do a cost analysis to analyze cost-benefit ratio. Next slide. So here is a drone video of the Klein Pond that was implemented on CD57. So as you can see on the bottom of the screen, you'll see the inlet of the pond, which is a concrete culvert, and a weir that restricts flow and diverts flow into the pond. Once the water elevation reaches the top of the weir, it'll flow and then bypass the pond itself. Otherwise, the water will be diverted into the pond into the sediment trap, which is the channel that you see within the pond itself. We design sediment traps and excavate them at a lower elevation than the pond bottom to help localize the sediment that deposits into the pond. And that's where we're seeing most of the sediment deposit that's entering the pond itself. This helps with reducing maintenance efforts and helps to keep the sediment localized in one spot. All right, next slide. We are also able to implement a two-stage ditch within the system, which is an alternative to a typical trapezoidal cross-section. So we have the inlet channel that conveys low flows and benches on either side of that help to dissipate energy. This channel design is a little bit more natural and creates more channel stability within the channel itself. So here are some photos from County Ditch 57 of the two-stage ditch that was implemented. We can see the benches that are located on each side, and then the one on the left is of the outlet, and then the one on the right is the upstream portion of the two-stage ditch. And lastly, we implemented a rate control weir at the outlet of the system. This is a notched rate control weir, which controlled flow rates during low flow events, and then also helped to maintain elevations within the channel to create linear storage within the channel and help to reduce flow rates at the outlet of the system.
The top of the weir was set just below the lowest tile coming into the system. So we had essentially extra storage in the bottom of the ditch that the landowners weren't using near the outlet. So that's the reason to put it where we did and the elevation that we did.
So for phase 2 monitoring, we narrowed the focus onto those 3 BMPs that I just talked about. We had 4 monitoring locations that were the upstream and downstream condition of each BMP to help compare and determine the reductions for each of those practices. First thing I'll talk about is flow. We did measure flow at each of these monitoring locations, and MSU provided all of the collection of monitoring and monitoring equipment. So thank you to them for that. We were measuring flow every 5 minutes for the duration of the monitoring season, and MDA did a model that helps to validate some of these flow rate measurements, as well as the DNR did secondary measurements on these to help ensure that the flow rate monitoring equipment was calibrated correctly. We collected over 500,000 data sets or data points for flow throughout the 2 years of monitoring. So we had quite a bit of data to sift through in this phase 2 of CD57 monitoring. So of those flow events, we actually monitored events based off of increases in flow. So if we saw a 10% increase in flow, that was considered an event. Of those events, in 2016, 15 of the events created reductions in peak flow rates, and in 2017, 18 of the events reduced peak flow rates of the 21 events that were there. So the events, we also measured how much were the flow rates reduced by. So each of these points within this graph represents an event that was measured, and then the green line represents the average reduction per year. On average, we're seeing reductions of around 25% of reduced peak flow rates through Klein Pond. Although you can see in the early spring months of when we're seeing frozen ground and reduced infiltration, we're seeing increases in peak flow rates. So that's the reason for those at the beginning of spring. We also looked at when was the pond most effective in terms of amount of rainfall. So we looked at intervals of 1/2 inch to 1.5 inches. And we can see that the lower events may not have had significant average reductions, although once we get to 1 inch and over, we're seeing on average those events being effective at reducing peak flow rates. And this is what we would expect, since during low flows, the outlets and channels aren't necessarily significantly reducing peak flows during those times. This is an example of an event, a specific event in October of about 1.2 inches of rainfall. The light green line here is the upstream condition of Klein Pond, where the dark green line is a hydrograph for the downstream condition of Klein Pond. When you look at the peak of the hydrograph, you can see that the peak flows have a reduction between 2 of those, which results in a reduce of peak flow rates due to the storage implemented on Klein Pond. As we move downstream and we have accumulated more water that's flowing into the ditch. The two-stage ditch there, that monitoring point, we're still seeing reduced peak flows from the upstream condition of Klein Pond. So we're seeing that even though it's downstream and there's additional water that's flowing into that point, that we're still having effects of reduction as we move downstream. In addition to the flow data that we collected, we also took water samples during those events and measured water quality parameters such as TN, which is total nitrogen, and TSS, which is total suspended solids. So for the Klein Pond, we saw that in 2016, we're seeing 8 of the 21 events reduce total nitrogen, and 15 of those events reducing TSS through Klein Pond of the 21 events that we measured. In 2017, there were 16 events, and of those, we saw 11 had reductions in total nitrogen and 12 had reductions in TSS. So we're seeing continued TSS, or on average, most of the events had reductions in TSS. Well, total nitrogen was kind of a mixed bag. There were some that had reductions and some that didn't have effects. So of those events, we can see, you know, how much did those events get reduced by. For the 2016, we saw on average 0.2 tons per event. And on 2017, we saw a capture rate of 0.07 tons per event, depending on, based off of that water chemistry data and flow rate measurements that we got from the monitoring data. We also looked at when was the pond most effective at capturing sediment. So although we do design these ponds for the 2-year event, which is, you know, 2+ inches of rainfall, when are we seeing the most benefits in terms of sediment, not necessarily quantity of water? And we saw that in the events of 0.5 inch to 1.5 inches is where we're seeing capture of sediment, whereas when we have less than 0.5 inch or greater than 1.5 inches, we're seeing exports of sediment within Klein Pond. So in addition to the water samples that we took, we also did surveys periodically throughout the lifetime of this project, comparing it to the as constructed condition in 2011 to the condition in
2014.
14 and 2019. There you go. So if we go to the next slide here, it'll show the profile where we can see that in 2014, we had buildup of sediment at the outlet of the system, and then not a ton of accumulation near the outlet of the system. In 2019, we can see that the accumulation has kind of equaled out and has reached what we would say its capacity is as the outlet pipe at the end of the sediment trap. It has reached that elevation of the outlet pipe. So as it continues to build up, a lot of that sediment is getting flushed out as we continue looking at this sediment buildup within the sediment trap. Overall, in the phase 1 monitoring, we saw 302 cubic yards of sediment accumulating, and then in the phase 2 report, we saw 109. So we're seeing that as the sediment trap continues to get filled up, its capture ability is being reduced. So we do have a total capture of 411 cubic yards over the 10 years that we've seen since its lifetime, since its construction.
In summary, we need to be creative with storage. We need to look at partnerships. When we have examples of success and have examples on the landscape that can help sell these things to landowners, and that's CD57 has been an important project in doing that. I've sent multiple landowners there that have witnessed it, talked to the producers that live around it, and have gotten on board for other storage projects. Funding is also important. Without funding, we wouldn't be able to do the monitoring that we're doing. There will be a report to the LCCMR that will be completed in the next couple months and be available. It'll also have more information on the maintenance of the system and what it costs to maintain that. So look for that. We'll answer any questions, but we want to thank all of our project partners, Blue Earth County, obviously ISG, MSU, the DNR, the Department of Ag, MPCA, LCCMR, and the Environmental Trust Fund. And thank you to MAWD for allowing us to do this presentation.